Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, Chemical Bonding. Today we will begin with lecture 13 from the course, but make sure you have watched the previous ones before viewing this one. So in this lecture, the topic for today's discussion is going to be polarity of bonds, wherein we are going to learn a very important term, that is dipole moment. So what do we mean by polarity of bonds? Well, you all know when we talk about bonds, we are generally talking about covalent bonds or ionic bonds. Covalent bonds formed by the sharing of electrons, ionic bonds formed by the transfer of electrons from one atom to another. Now, there is going to be no covalent bond or no ionic bond which is going to be totally covalent or totally ionic. As far as ionic bonds are concerned, we have already studied that the ionic bonds, they are not totally ionic. There will be always a partial covalent character in that, and that we have discussed quite in detail while we were discussing the Fajans rule. Now coming up to the covalent compounds. So the covalent bonds, they are also not going to be totally covalent. There will be always some partial ionic character attached to that covalent bond also. That is less or more, that is going to depend upon certain things, but definitely all covalent bonds, they are going to have some partial ionic character, and that is what is going to lead to the polarity of bonds that we are going to study in this lecture. So are you ready to study this very interesting topic? So, as I told you, no bond is going to be either covalent complete or either ionic complete. So, let us consider over here a covalent bond that is going to be in the case of a hydrogen molecule, that is between two hydrogen atoms, and you will say that these are two hydrogen atoms. So hydrogen atoms, they are sharing their electron pair, right? Both of them, they were electron deficient. They had one electron less to complete their duplet, and they placed their electrons in the center, and now their duplet is going to be complete. And because they both are same hydrogen atoms, right, so they are going to have an equal sharing of this electron pair. Neither of them is more electronegative than the other. Okay, so then how can we say that this bond also will have some ionic character? Well, it can have some ionic character. That is what we are going to study. In fact, not only the hydrogen bond, but the bonds between any of the homonuclear molecules. For example, we have O2, Cl2, N2, F2, where there is equal sharing of the electron pair between the two atoms. In that cases also, when although we say that these are going to be non-polar covalent bonds, but there is going to be some ionic character attached. Why is it so? You have to understand, and you have to go back to your quantum mechanical model. Have you always studied that the electron is going to be static? No, it is not going to be static. The electrons, they are always moving. So we have this shared pair of electrons present in the orbitals which were overlapping, but the electrons, they are moving. So there can be an instant of time when one of these electrons, say this electron from this hydrogen, this moves more towards this hydrogen. At that moment, there is going to be a partial negative charge on this hydrogen and a partial positive charge on this hydrogen. It can be the other way around also, that the other electron from this hydrogen gets displaced more towards this hydrogen. That is there. But for a fraction of a second, it is possible that one of the two hydrogen atoms gets a partial positive charge and the other a partial negative charge. And that is what all is ionic character. Right? So whenever a partial positive and negative charge has been created in a bond, that is what we are referring to as the polarity of bond. Okay, but for practical purposes, the homonuclear molecules, we are going to call them as non-polar bonds. Okay, so the bond between them, we say it is formed by the equal sharing of the electron pair. So this is a non-polar covalent bond, but even then there is going to be some ionic character always attached with it. Okay, I hope this point is very much clear to you people. Now this is the case when we talk about the homonuclear molecules. Let us discuss what about the heteronuclear molecules. In the case of heteronuclear molecules, like we have HF, the shared pair of electron is going to be placed again in the center of the two atoms, but now one of the atoms is going to be more electronegative than the other. In HF, you all know fluorine is the most electronegative element or the atom when we are discussing the periodic table, and hydrogen, this is going to be the most electropositive non-metal. Okay, now, when a bond is being formed between the most electropositive non-metal and the most electronegative non-metal, what is going to happen? The electronegativity of fluorine is more. So this is going to pull the electron pair more towards itself. And in the result, what is going to happen? We are going to have a partial negative charge on fluorine and a partial positive charge on hydrogen, and hence a polarity has been created. What do we mean by a polarity? It is basically that there has been a charge separation. Okay, if these two electrons would have been equally shared, there was no charge separation. Now we can see that the charges have separated out. One is having more electron density, one is having less electron density, and poles have been created. Poles have been created. There are different charges, and these charges, they are separated from each other by some distance, right? So now when we have a polarization being created, we say that the molecule possesses dipole moment, and this dipole moment, this is denoted by a symbol that is mu. Okay, this is how we write it. And this mu, or the dipole moment, this is the product of the magnitude of charge and the distance between the centers of the positive and negative charges. So we will now understand in detail what is this dipole moment. So now you have seen in the case of the HF molecule, there is a separation of the positive charge and the negative charge. And whenever there is going to occur a charge separation in a covalent bond, this results in the formation of an electrical dipole. Dipole means two poles, and these are two electrical poles, meaning that we have a bond, and on one end of the bond we have a positive charge, and on the other we have a negative charge. So these are going to be two equal but opposite charges with a small distance between them. And each electrical dipole is characterized by its dipole moment, which is represented as mu, and this mu is equal to the magnitude of charge q into the distance of separation r between them. And now one very important thing, that dipole moment, this is a vector quantity. Why is it a vector quantity? Because this has a direction attached with it. It will have some value, but along with that value we have a direction. What is the direction? The direction is towards the more electronegative element. The electron density is more towards the electronegative element. So we have a magnitude of dipole moment and magnitude of dipole moment towards the more electronegative atom or the element. So dipole moment is a vector quantity. So what all we are going to calculate, although we are not going to do the mathematical calculations for dipole moment, but you will be able to understand that when we are adding up various dipole moments of various bonds in a molecule, this addition is going to be a vector addition. Okay, so this is a vector quantity, and this is measured in the unit debye. Debye denoted by the letter D, and the SI unit is going to be coulomb meter. Coulomb for the charge and meter for the SI unit of distance, that is meter, right? So we have coulomb meter, and the cm is going to be short form for it, but this is not centimeter because this is not a small c, we have a capital C given for the coulomb. 1 by this is equal to 3.33564 into 10 power minus 30 coulomb meter. And a very important thing, that the dipole moment, this is going to depend upon the difference in the electronegativities of the two bonded atoms. More is going to be the electronegativity difference, more is going to be the dipole moment of that bond. So the presence of the dipole moment, this is represented by a crossed arrow. Here you can see we have a arrow and we have put a cross on it. And this is going to be put on the Lewis structure of the molecule with the cross on the positive end and the arrowhead on the negative end. So this arrow, this will be on the negative atom, and this cross, or you can say the plus sign, as you can remember, this will be on the electropositive element. So you can that also easily remember, positive, positive. The arrow symbolizes the direction of the shift of the electron density in the molecule. So in the HF molecule, so this is the Lewis structure, and this is how we represent the dipole moment, that this is going to be a shift of the electron density towards the more electronegative element, that is fluorine. So now let us consider one more term, that is bond moment, right? Bond moment is the dipole moment of a particular bond, and dipole moment of a molecule is going to be determined by the bond moments of all the bonds, right? So one dipole moment of one bond, that is called as the bond moment, and when we are going to have a vector sum of all the bond moments of all the bonds in a molecule, we will be calling it as the dipole moment of that molecule. For a diatomic heteronuclear molecule, the bond moment will be equal to the dipole moment because there is just one bond. For the diatomic homonuclear molecules, the bond moment is going to be 0 because there is no shifting of the bond pair towards any atom, and as Q is going to be 0, so the dipole moment, which is a product of Q into R, that will be 0. For the polyatomic molecules, the dipole moment, this is equal to the vector sum of all the bond moments and lone pair moments. Now what is this lone pair moment? Let us understand this also. So now what is this lone pair moment? Well, you have drawn the Lewis structures, and in that you have seen that along with the bonded pair of electrons, there were present lone pair of electrons also. So if there are electrons, whether they are bonding or they are non-bonding electrons, they are negatively charged particles, and they are going to contribute towards the dipole moment, and hence the contribution of the lone pair of electrons, if present on any atom of the molecule, towards the dipole moment is going to be called as the lone pair moment. Now, the lone pair does not make any contribution to the dipole moment if the lone pair belongs to a pure S or a pure p orbital of the bonding atom. Why? Let us understand that also. If the lone pair is present in the s orbital, if you remember, the s orbital is a spherically symmetrical orbital. So the electron density is going to be equal in all directions, and if there are going to be two electrons, they are going to cancel the effect of each other. Similarly, if there is a p orbital, so the two lobes of the p orbital, they are directed opposite to each other. The electron density in these two lobes, that is going to be equal, and therefore it is going to be the cancellation of the charges, and hence we will not be having any dipole moment because of these two electrons present in the p orbitals. Okay. But now, when we consider the lone pair to be present in a hybrid orbital, the electron density is not equal in the two lobes, therefore it is going to contribute to the dipole moment. Well, you will be asking me, what is this hybrid orbital? Do not worry, you will be understanding this in detail in the coming up lectures, but for now what you can consider is that this is the shape of a hybrid orbital. Okay, so there are two lobes, one lobe is having a bigger size than the other one, and hence this is going to have more of an electron density than this Okay, so there is going to be a dipole in which direction? It is going to be in this direction, because here we have more of electron density than this portion of the lobe, right? So if a lone pair is present in a hybrid orbital, the density is not going to be equal, and hence it is going to contribute to the dipole moment, as you will be seeing when we will be discussing the examples related to the dipole moment. Now the value of the lone pair moment is going to depend upon the S percentage S character of the hybrid orbitals. As you will see in the further lectures, there are going to be different types of hybridization, that is sp, sp2, sp3, and more is going to be the S character of those hybrid orbitals, more is going to be the value of the lone pair moment. And as the S character is going to increase, the lone pair moment will increase up till 50%, and then it falls, because after 50%, the orbital is going to have much more S character. It is becoming more spherical and hence more symmetrical, and therefore there is going to be less of the lone pair moment. The lone pair moment for the hybrid orbitals is going to be maximum for sp, then sp2, and then sp3. So if you consider a percentage, okay, so we have an equal percentage of S character and P character. So here it is 50-50%, and then it is going to fall down, because then it is going to be 2 parts of P and 1 part of S, and here it is going to be 3 parts of P and 1 part of S, so coming up to 25% of S character, right? So the lone pair moment, as we discussed, that it is going to be more where there is S character is more. So maximum lone pair moment for the sp hybridized orbitals. What these orbitals mean, you will be understanding later in the course coming up. Do not worry about, but this is going to happen, and this is placed over here so that you can, when you're revising your lectures, at least that time you can understand these things very well. Now generally the lone pair moment, this has larger magnitude than the bond pair moment. That means the dipole created because of the bonded electrons is going to be less than the dipole created by the lone pair of electrons. In the hybrid orbital of carbon, this is going to vary from 4.4 d for a sp hybrid orbital to 3.7 d for a sp3 hybridized orbital. Some largest values of bond moment you can see over here. From phosphorus to boron, this is going to be 4.4 d. Then nitrogen to oxygen, it is 4.28 D, and oxygen to boron, this is 3.60. So these are some of the values of the largest dipole moments in a single bond. Most other bond moments are going to be less or much less than these values. So polar diatomic molecule, as we've already discussed, this consists of only one polar bond. So the dipole moment of the molecule, this is equal to the polar bond itself. So if we have a HCl molecule, the Cl part is going to be more electronegative than the H. So we have a partial negative charge on chlorine and a partial positive charge on hydrogen. And the dipole moment of the HCl bond, that is 1.03 dBi. Similarly, the dipole moment of HCl molecule will be equal to this only, and that will be 1.03 dBi. So the polarity of any bond, this is going to be measured by the dipole moment, and in case of a diatomic molecule, we can just find out the polarity of the bond by the electronegativity difference also. The ionic character will be directly proportional to the electronegativity difference between the two atoms. And the percentage ionic character, this can be given as 16 into ENA minus ENB plus 3.5 into ENA minus ENB. These ENA being the electronegativity of atom A and ENB the electronegativity of atom B. And if the percentage ionic character is 0. This is going to happen when then these two electronegativities of the two atoms, they are equal, and this we are going to call as a 100% covalent bond. Although now you know that this is not 100% covalent. At any instant of time there is a presence of a partial ionic character also, because of the constant moving of the electrons. Then the percentage ionic character, this can be between 0 to 15%. When it is going to be between 0 to 15%, we call it as a non-polar covalent bond. When the ionic character is going to be 15 to 50%, we call it as a polar covalent bond. Greater than 50%, we are going to call it as a ionic bond. Now, the calculation for the heteronuclear molecules, where there are diatomic molecules only, the calculation of the dipole moment becomes easy. But when we have polyatomic molecules which are going to contain more than one polar bonds, it is not going to be the simple value of the bond moments. The dipole moment is going to depend upon the individual dipole moments of all the bonds, which are called as the bond dipoles, but it will be also dependent upon the spatial arrangement of the various bonds in the molecules. Okay, so how these bonds they are arranged in the molecule, that is going to be very important, because you know that dipole is a vector quantity. So the dipole moment of the molecule, this is going to be the vector sum of the dipole moment of the various bonds. For example, we consider a water molecule. So water molecule, we have a bent structure. The two OH bonds, they are oriented at an angle of 104.5 degree. And if you see that we have a oxygen which is a partial negative charge, a hydrogen which is a partial positive charge. So the direction of the two dipoles is this. So we will be having a net dipole moment. These two are going to give us a net dipole moment of 6.17 into 10 power minus 30 coulomb meter as the resultant dipole moment of the two OH bonds, and that is simply because of the addition of these two vectors. Okay. So that would be all for this lecture. We are going to discuss many examples of the dipole moment in various molecules. This will help you understand this concept very well. We are going to discuss it again in the applications of dipole moment. What you have understood in this lecture is basically what is dipole. Now we are going to actually put into practice how we are going to use the information of this dipole. Okay, so this is going to be a really very interesting lecture. So please do subscribe to the channel if you have not done till now, and also click on the bell icon so that you get a notification as and when we put up the new lecture for you, because this course is going to be really very important for you. Okay, every bit of lecture, every lecture, this is going to be very important. Any doubt, please feel free, mail us at h2ochemistry@gmail.com. Also, you can put the doubts in the comment section also. You are most welcome with all your doubts. Please do clear them so that your concepts are very clear. If you like the lecture, please do click on the like link before you leave. See you again. Have a nice time. God bless you.